So I'm back with this little project of mine. I'm going to, if I could see the damn thing, I'm going to use a small blue diamond to punch that hole in a little more. I don't know if I got it or not. It's got to come up out of the liquid a little bit so it doesn't sink, right? Push it some more. Hey, there they go. All right. That's pretty good. Might work. So, when you whack on a diamond like that, you know what it does? Absolutely nothing, man. That was already there. Sorry. These are not like, perfect because they're not meant to make $1 bazillion with, right? Somebody cut these and they sold this to me as, I think, blue topaz. And I think I bought a kilo of them or something for just over $100, something like that. Very expensive. I really stepped up to the plate. This is bigger than the current Hope Diamond, by the way. Much bigger. This is almost 100 carats. Okay, so, and you can use it for all kinds of shit other than making $1 bazillion, so I do. Because that's what they're for. That's what they're for. This is actually going into my space-based laser system. Okay, so, or maybe I'm going to use it for milling and machining too, diamond lasers, and this will collimate the beam. When you see an LED, a light-emitting diode, it's a lasing diode. It emits one wavelength of light. But we don't collimate most of them. Collimation is narrowing it down to one small beam. And so the beam that comes out of there, and I'll polish the tip of it. So it's, got like a lens shape, right? So I can focus it, but I can do that really, 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 really small. It didn't hurt my diamond at all, did it? I can whack on them. I can light them on fire. I can torch them. Doesn't touch them, man. They are impervious to heat, and I can hold this in my hand and drill it, cut it, polish it without water. Not use water at all. And you try that with a piece of metal, it lasts about 2 seconds, but not even that long, before you have to let go, unless you got gloves on or something. And most rocks, I don't know about that, but metal anyway, and some rocks get pretty hot. They do. So it's a property of diamonds that they absorb heat. Metal passes heat without resistance, but resists magnetic fields. Okay, and that resistance is what makes it stick to a magnet. Doesn't let it pass through. This is transparent to a magnetic field, which is why it's so clear. Right? Light is a magnetic energy. It's not bright, flashy things. It's an absolutely invisible thing, because this over here and everything in between has light. from the stone, but you can't see it. Right? There's nothing there. My finger doesn't turn blue. On this side, it might. On this side, it might. Okay, see? Light passing through turns blue because the planes of cleavage are so close together. The light goes between those planes of cleavage, right? Bump, 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 bump. And they're half the size of this particular shade of blue. So that when it bounces up, it's half a wavelength, and it bounces down, it's the whole wavelength. Huh? So you see how that works? And they're traveling that way, towards the point, along planes of cleavage that parallel this pavilion here. So that's why they sparkle on the outside. And when I send a laser beam through here, and we're talking a laser beam, a big sucker, I can make it all of that, neck it down to that size of a point. Wow, huh? So then I can cut metal with it. Boom! See, it's lasing already, and that's just with the little light in my lamp here. They are beta emitters, okay, because of the carbon-14, and that means when the light hits them, the carbon-14 has one extra neutron. And it wants to be stable with 13 everythings, 6 carbon protons. A proton and an electron are a hydrogen atom. Okay? So each proton was a hydrogen atom to begin with. Has to be, because that's where everything starts, and then they get squeezed into a star. Okay? And these build up, these crystals, in molten rock. And they start from the small end and build up. They build as the molten stuff cools. And so the crystal gets bigger and bigger and bigger and bigger as it goes along. And the more carbon there is there, the bigger the crystal gets. Now, in a kimberlite pipe, it's just a cone of compression underneath of an asteroid, right? It only goes down a little ways, and it's only minerals in place. It doesn't have the molten rock from the semi-molten mantle feeding it. It's already hard crystals, some of which are calcite, some of which are fluorite, which both have carbon in them. Okay? And the carbon, the fluorine and the calcium and sodium vaporize. Aluminum, it vaporizes. It's gone. It's not like gone, but it turns into other stuff. Because as the molten rock cools from underneath the asteroid strike, and it does, as it cools, the first thing out of the melt is the carbon. That's how everything works. That's why molten rock coming up from the semi-molten mantle has carbon that precipitates out first. It's not rare, it's not hard to find. We are carbon. We're carbon, all of us. And just about everything in our body that's not water is made with some form of carbon. Our bones are calcium, kind of like calcium carbonate, huh? Like shells. And they are like the bones of the earth, and they're our bones. And everything in us is made not by magic, but by chemistry. Our bodies are chemical factories made out of carbon, because carbon is a semi-metal. It's halfway in between metals and the non-metals like oxygen and sulfur, chlorine, that sort of thing. And the metals use the non-metals, like oxygen, to stabilize, right? To provide those extra electrons that they need to get 8 electrons into the outer valence orbit. Carbon joins together and they've only got 4 electrons. But when 2 carbon atoms come together, it creates that stability of 8 electrons in the outer valence orbit. So this carbon is the stable carbon. Carbon-12, the stuff we deal with on the surface, burns, right? Like coal. And if I put a torch to my graphite crucibles, the inexpensive ones anyway, they don't have a clay in them to even the temperature out and keep it from burning. They'll burn right up. I can put a torch to them and they'll burn right up. I can put a torch to this and it just sits there. It'll glow white hot, just hotter than the sun. I mean, whiter, brighter than the sun. But it won't melt. I've tried. I have tried mightily. I can get a flame on my plasma cutter that's 3,000 degrees Celsius. Doesn't touch it because it doesn't melt until 3,800 degrees. 100 degrees Celsius is the difference between the freezing point of water and the boiling point of water. 100 degrees. Those increments are bigger than the increments in the Fahrenheit scale. And 100 degrees is a pretty big jump for us, because our body doesn't pass heat without resistance. We get burned because there's water inside of us and other things. And the carbon-12 has a missing neutron, right? It's wants to become carbon-13, and so it's absorbing energy, and that's why it's black. Oh boy. Did I drop it? I bet I did. Oh boy. Oh, there it is. And that's why black diamonds are black. Because they have more carbon-12 in them. Not all of them. They're still clear, right? You can see through them. And it's not just because they're squeezed together. It's because all populations of carbon have all 3 isotopes. There's carbon-12, carbon-13, and carbon-14. Carbon-14 is trying to get rid of the mass of that extra neutron, and it emits the mass of an electron, about 1/80,000th of the mass of a proton. So it doesn't take much. But it's fission, right? It's not just a chemical reaction. It's a nuclear fission at the most basic level. And that mass comes off of there at the speed of light. And that's what those bright flashes are you see there. It's what makes diamonds so darn bright, because that extra neutron wants to become a proton. And when it does, it turns into nitrogen. Right? It goes from carbon-14 to nitrogen-14 because the extra neutron in carbon turned into a proton. by losing the mass of an electron. And you know what? I'm not making this up. I read it in a book. Okay, we already know about it. It's not new science, and you may not know about it, but other people do. I didn't make it up, man. I did not make it up. But anyway, I've taken it somewhat further with other things because I find the same thing all around me here in the Sierra Estrella. And in fact, to see things that bump bits and pieces of uranium that form in the silicon carbide and aluminum oxide of the mountains behind me, and they're spaced around like in a hexagon, like this, bum 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 bum. You didn't know that was there, did you? I did. That's what those are, little hexagons around the periphery. Because it's cubic hexagonal. Cubic in one direction, and you rotate it 90 degrees, and it's hexagonal in the other direction. It's the stacking order, right? And it depends on which way you look at it. But it's the same thing, because they're squeezed together as tightly as they can be. And they carry the heat somewhere other than outside of them. They absorb heat. And that's what makes them so special, because we can use them for bearings. There's lots of them. They're not rare, right? They're not rare. Get over the idea that the De Beers Corporation has been telling you the truth. They're not rare. They're not hard to find. And they're beautiful. They are beautiful. There's no doubt about it. But they come from every fault line on Earth. Maybe not gemstones like this, but they will. Every creek, river, dry wash in the entire world is a fault line. There are other fault lines from previous incarnations of this particular rock. The continent of the United States turns in a counterclockwise direction, as does the Eurasian continent. The continents on the south side of the equator turn clockwise, because the Earth is turning from west to east, and they kind of roll along with it. And it's a mechanical thing, right? They're rolling along. The Earth is going this way, and they roll this way. See what I mean? So the northern ones roll that way, and the southern ones roll the other way. So that's why they do that. And as they go around, California is on the Pacific plate. It rides up over the North American plate. It's going the same way, right? It's also turning that way. So they turn against each other. And it subducts the rocks that are up here underneath and provides billions and billions and billions of pounds per square inch, more than anything else. And when that molten rock starts coming out the other side over here on Arizona, and that's what Baja California is, or the Gulf of California, between Baja and Mexico, and then Mexico and Arizona are North American continent. And I have diamonds here in the Gila River. It's a fault line that goes all the way down to the semi-molten mantle. So it's 10 times deeper than the deepest kimberlite pipe. Over 10 times deeper. And much more pressure, and of course, an almost unlimited amount of carbon. And when it comes up at 3,800 degrees, there's nothing else solid. It's all vapor, everything. There's no water, there's no iron, there's no anything, just carbon. And that's why we find carbon crystals so clear, because there's no contamination inside them, and they have double covalent bonds. So it looks like that point of that pavilion is right next to the surface here, and it's not. We see through it because it is transparent to magnetic energy. And they're tough, tougher than anything else. I watched a video of my friend in India taking one of these diamonds. It was a little smaller than this. And he pounded it into a piece of what looked like aluminum or something like that, probably aluminum. But he had on his workbench. Took a hammer, a steel hammer, like I just used, and pounded that thing in, and then went, ha ha, look at that, far out, in Hindi or something. And I was mightily impressed, and I still am, because these are going to help me change the world. We can build machines that don't break. And I'm building some now that won't fall out of the sky with your family in them, or my family, because I love them, yours and mine. Peace.